All right, welcome to week 11. We're going to talk about kind of two closely related things. They may seem a little disjointed from what we have been studying, but we're going to focus on section 4.1, which has Taylor polynomials and all that sort of stuff in it, and Taylor's theorem in general for multivariable functions. And then in 4.2, there's literally a page that we're going to talk about, and then add some things that are not in the textbook into that part when we get there. Okay, that's Sylvester's theorem when we get there. Right? And then just a note that in the Taylor polynomial section, we don't do any higher order stuff or the remainders, so that's two different sections in the textbook that we're not going to cover. Okay, so I said Taylor polynomials, and you're probably thinking to yourself, what are those things, right? And so we might need to flip back to Calc 1, but we were just saying that in Calc 1 that we have a function that's has its derivatives all continuously differentiable. We have a point in the real numbers, and then we say that the Taylor polynomial of degree n, right, is p sub n of x. And what it is, it's the best approximation of f at a. So that's sort of the spirit in which we're going to go forward, is that this is a Calc 1 case, but really we're going to do this to try and approximate a surface. Okay, and so we said that for p1 of x, we had the point plus the derivative at a, and then times x minus a. This looks awfully a lot like a tangent line, right? And so then we can continue going on, and then for p2 of x, we have f of a plus f prime of a, and then we're actually going to also introduce a factor of, factor of 1/2. Let me just get rid of that shade. So this would be 1/2, and then this would be the second derivative evaluated at a, and then times x minus a quantity squared. Okay, and then similarly for p3, we would have f of a. So it's actually each polynomial as you go up, it includes the previous one. So f of a plus f prime of a times x minus a, and then plus f second derivative at a over 2 x minus a, and then squared. And then the new part here is going to be plus f third derivative evaluated at a over 6, and then x minus a quantity cubed. Okay, and so each time really what you're doing for the nth derivative, it should be the previous Taylor polynomial plus kind of this factor of f to the to the nth derivative evaluated at a over n factorial, and then times the corresponding factor of x, so x minus a to the nth. Okay, so what we can say here is that in general, this is going to be the sum from I is equal to 0 to n, and then f to the ith derivative, that's an I, okay, and then of a over I factorial times this factor of x minus a to the ith power. Okay, so then just as a quick example here, what I'm going to do is find a few Taylor polynomials for this function at this given point, or this given center is what the language we used back in Calc 1. So if I might need to just do a few derivatives, so I'll just do f prime quickly here. This is 2x e to the x squared, and then f to the second derivative is going to be, well, we have to use the product rule, and we obtain 2e to the x squared, and then plus 4 x squared e to the x squared, and I'm skipping the third derivative and I'm going to the fourth. Actually, you would just use 4. Okay, and you end up getting 4e to the x squared, and then parentheses 4x to the fourth plus 12x squared plus 3. Okay, and I'm not going to lie, I use Wolfram Alpha for that. Okay. All right, so then if we're looking at the Taylor polynomials, then I'm going to have P1, and this is just going to be, well, f of a. So f of a, so let's see, what is it? Let's see, 1. And then plus, and then if I evaluate the derivative at 0, I just get 0, so that's really boring. P of 1 is just 1. P of 2 is going to be that previous one, and then I have to evaluate the derivative at 0, and I end up just getting 2. But then I divide by 2, that n, the n factorial, so 2 factorial is 2, and then just have that quantity x minus a, which is, and a is 0, so let's put that in there, and square that. Okay, all said and told, we get 1 plus x squared. Okay, I encourage you to pause the video and just find P3 and and P4. That's a 3. Okay, so pause the video, find those, and then resume when you're ready. All right, and if you did pause this, you'll find that P3 is actually just P2, and then P4 is going to be, after you simplify, 1 plus x squared, and then plus 1/2 x to the fourth. Okay, and so we can visualize that in GeoGebra, and so I did place a GeoGebra file in the Google Drive folder if you want to view it. And so here I have the original function, and then I can leave that as it is, and then I can enable P1 of x, which is just that point, right? And then P2 is just 1 plus x squared, so our basic garden variety parabola. Okay, so you can see as I increase the degree of the Taylor polynomial, I'm getting a better approximation. And then here, I'll re-enable that again. So as you can see, when I go to the 4th degree Taylor polynomial, I'm getting even closer to the function. Okay, so that's kind of the upshot of Taylor polynomials. Okay, and then just what do we want to do, and how does this connect? So again, the idea of a Taylor polynomial is that we can get a nice approximation. Okay, and so sometimes the derivatives could be challenging, or finding the linearization there or at a point could be, a nightmare. So we might just want to say, hey, let's differentiate and get pretty close, and at least when we're pretty close, we have some idea of what's going on. And so how does this connect? Well, this is the idea we were trying to, previously we were trying to do like tangent planes and all that, and get a good representation of a function. So we're just going to continue to get that approximation of a surface now. Okay, so in the next video we're going to kind of dive into Taylor polynomials and how they extend into multivariable functions.